here in the first row.
The best seats.
All right. Welcome to the Physics Colloquium. It's such a big pleasure for me today to introduce our speaker, Klaus Mølmer. Klaus is an outstanding and inspiring quantum optician. I mean, his work in quantum optics, atomic physics, and quantum information has inspired the field in a way that you cannot imagine. So, oh, okay, sorry, I'm gonna have to repeat again. Is that okay? Okay. So I'm just going to repeat and say that it's such a big pleasure to have Klaus Mølmer today as our colloquium speaker. As I was saying that Klaus has been a person who has inspired the field of quantum information, atomic physics, and quantum optics. He has developed very powerful tools to understand open quantum systems. And moreover, he proposed in 1999 a gate that is called the Mølmer-Sørensen gate with his student, or was postdoc at the time?
Student.
And this gate has been adapted in all trap ion experiments and is the leading gate for implementing quantum gates for quantum computers. So Klaus is from, now he's working at the Niels Bohr Institute, and he was before in the University of Aarhus, where actually he did his PhD at the University of Aarhus, but I was looking and he very quickly, he did a postdoc at the Max Planck Institute, and then he was telling me that he got an offer, a faculty position almost immediately after he graduated from his PhD, but then he went to as a senior investigator or young professor to work with Alan Aspect, the Nobel Prize, and he then went to work with Peter Solar in Innsbruck. So the important part and the nice part is actually he's here for about less than 3 weeks, but he's going to be here for a longer period of time. He's sitting at Gila in an office next to June's office. So feel free to contact him if you are interested in talking to him. And with that, I'm going to let him speak today about from quantum optics to bits and pieces. Thank you.
Thank you very much. Thank you very much, Anne-Maria, for the very, very kind introduction. It's really great to be back here. I was at Gila about 20 years ago, actually a couple of times over a couple of years. I gave a talk. I think the last presentation I gave here was on the same topic as I will talk today, but there has been both some new components into the work that I will discuss, and it was a special conference actually organized by Peter Solar, who was here as a fellow at that time. So this is really a place I like, and it's great to be back. I was looking forward to come here ever since this fellowship was set up for me, and the first few days here, people coming into my office and saying hello. It's really wonderful. Of course, after COVID, we're also still very happy to see our old friends through many years, and I also have to say it's a bit emotional for me to also be here and see so many colleagues again after so long time. So I will be talking about a special topic within quantum optics. And in fact, it's not because I'm a very important person, but I'd like to share with you the way I was introduced into this field, because I'm the kind of physicist who is very motivated. I actually like all the physics I do. I feel really attached to the physics I do. I think it's something that's important. I want to see the answer to this question, or I want to find a really clever question, and as soon as I have one, I really want the answer desperately, because I think that's fun, right? And then, of course, sometimes you get the referee reports that prove that I'm the only one interested in the answer to that particular question. But I still keep moving on like that. So I want to tell you why I'm in quantum optics. So an outline of this talk is how I fell in love with quantum optics. And there's a special aspect of quantum optics that will be the theme of this talk, and that is the dynamics of monitored quantum systems. So that's systems that we are looking at all the time, and they don't die, they don't disappear, because we have modern methods to actually look at systems that keep their quantum states alive, but of course evolving due to these measurements. And then in the end, I'll tell how the particular method we're using for that has also developed into a theory for sensing. So of course there are experts, world experts in sensors at this particular institute, and I will tell you about the special take on sensing where you use the full measurement records looking at a single quantum system to learn something about parameters of that quantum system or what influences that quantum system. Could be a magnetic field, it could be a perturbation of some kind. But anyway, how did I fall in love with quantum optics? Well, let me first do a mini historical review of what is quantum mechanics, because my background was, of course, to study quantum mechanics. So I learned first about Planck's old quantum theory. In the year 1900, Planck quantized radiation. He concluded that the radiation energy, or at least the way radiation energy is exchanged with matter, is in units of quanta energies, which is Planck's constant times the frequency of light. And Einstein, 5 years later, was bold enough to say that light are actually these quanta. The light is composed of quanta of light, what we call photons today, and they have a wave nature, but there's also these units of energy. And Einstein already had a concern because he also believed in the wave theory, the Maxwell theory, of course. So when you have only one quantum and you send it towards an array of detectors, only one of these detectors can actually fire and absorb that photon, and then it's gone. And Einstein really didn't like that. What happens with the wave, the electromagnetic field in the rest of space, when one detector clicks and then you have just vacuum in front of all the other detectors? And this is, of course, kind of interesting. It's a 1905 article, and it's almost prophetic compared to the later discussions about interpretations of quantum mechanics, where we have exactly the same question: what happens when you do a measurement on a quantum particle? So Einstein was concerned about this issue from the very beginning. Then the next thing that happens, at least in my version of the story, is Niels Bohr, not only because he's a Danish physicist, but also because he made the Bohr model of the atom. And the model of the atom is the one where the electrons are in planetary orbits, according to the Coulomb forces, but only certain orbits are allowed. And that's a magic trick, but it's also just a postulate, of course. It was not a real theory by Bohr, but he postulates these orbits in such a way that the energy occupied by the electron in each orbit have differences from orbit to orbit that corresponds to the energy of the photons. And these photons are exactly the ones that are being emitted when the electron jumps from one orbit to the next one. So this is, of course, also what we all know. And Bohr had a trick up his sleeve, actually. It's called the correspondence principle. So for very large orbits, he wanted the transition frequencies to be the same as the orbital frequency, because a big radiator radiates at the frequency at which it moves. And that criterion, together with Kepler's laws of motion, actually led to a formula, which is the 1/n² formula for the energy levels, which, according to Bohr, should at least be true for large n, but it actually holds all the way in, which is magic. But that's true. So Bohr has this formula. He identified the Rydberg constant, and the formula is analytical, and it gives actually the frequency spectrum with 5-digit precision, which was absolutely fantastic at the time. And if you take into account special relativity, you can boost it up to 7 digits of precision. Now, a big disaster, if you take any other atom but hydrogen, it's really wrong. It's off, and it was off by 10 to 15% for helium. And the answer to that riddle, well, it took like 10 years for Bohr to realize. So he was fighting with students and postdocs to actually make complicated orbit theories that could reproduce the two-electron problem of helium, and they couldn't make it work. And finally, Louis de Broglie, French physicist, said maybe we should look into the argument about these orbits. Maybe it's not really orbits, but maybe wave-type boundary condition that defines the circumference of these orbits. So this, just mentioning the word wave, was enough to make theoretical physicist Erwin Schrödinger sit down and write a wave equation. So the inspiration for the wave equation was really that you were looking for something wavy-like. And then he tried a few equations, and what is special about the Schrödinger equation is that it's first order in time and second order in space. So his first attempt was actually second order in both, but that didn't work for his purpose. It's actually the Klein-Gordon equation, so it works for other purposes. But this is the one we all know and love, and here's Schrödinger, and here are some pictures of hydrogen wave functions, which are the eigensolutions to this equation. And we all know that these equations come with a complex phase evolution, which is equivalent to the energies of these states. And these are exactly the same energies as in Bohr's calculation. But now they come from a different theory, and a few years later, a Norwegian scientist did the solution of this problem, approximate, of course, but for helium with 2 electrons. And he got the helium spectrum with 1 per mil precision with an approximate method. So this is, of course, the wonderful Schrödinger equation. Now, you may wonder why there's a picture of Olivia Newton-John and John Travolta here, but Olivia Newton-John's grandfather was a German scientist called Max Born. And I'm not kidding. She is a grandchild of Max Born. And Max Born taught us was that the wave function themselves have shapes. And these shapes have well, it's still being discussed to this very day what the wave function means. But at least one thing we all agree upon is that when you do measurements, you get random outcomes. And the random outcomes occur with probabilities. And these probabilities are the square of these wave functions. Okay? Then whether there is a true wave function that collapses or it never collapses, but we are in a many-world scenario where everything happens, all of that we can discuss in the next 2 weeks. But Born's rule is the one we see in the experiment. You do your experiment, you get random outcomes, and the probability distribution is governed by the shape of this wave function. So that's really what Born said. And again, Einstein comes back in. He doesn't like it too much. If quantum theory is correct, it signifies the end of physics as a science, was one of his conclusions, because it's not only the randomness, but it's also the way that correlated particles, what we call entangled particles today, measurements on one infer what you will measure on the other particle, even if there's no physical communication between them. So he didn't like it. Schrödinger liked it even less, and he was happy with the theory using probabilities and mean values, but he didn't like what he considered to be mere speculation about what a single quantum system does. Is there randomness taking place in every single measurement? It's certainly true that if you do billions and billions, you get mean values, but they are not random anymore. Then they are very good mean values with high precision. And Schrödinger, he tried to save the theory by saying it's not about single experiments, it's only about many experiments, because we will never do a single experiment with a single quantum system. 1952, it's fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. And this is the ichthyosaur. It's not only a dinosaur, it's a fish-like dinosaur, which is probably even harder to raise in a zoo. So Schrödinger is, of course, a genius in terms of, I always loved Schrödinger. I mean, he's a guy with a cat, right? He just knows how to put things in perspective. So he thought we could save theory, and we know now that this didn't hold, right? Today we are doing experiments with single atoms, single molecules, and whatnot, and people love to make fun of this quote, but I think it's also a beautiful quote, actually, and deep insight. So Schrödinger's equation works, and of course it has been used all over quantum mechanics with the suitable adaptation to what system you're looking at, all microscopic physics. We are solving typically with the perspective of getting mean values out, average properties. Typically when you do atomic physics experiments, you do it on billions and billions of atoms, and you measure cross sections or energies and whatnot, and the same in particle physics and all the way up to solid state physics. So the shut up and calculate idea that we just calculate things and leave the philosophy for others or the past, of course lives in many fields of physics. But in our particular field of physics, we are approaching the single quantum system again and again, and that means we have to reflect just a little bit upon what is actually happening and how do we describe this quantum system. So this is where quantum optics entered, and I'll say a few words about quantum optics. There's a quantum theory of light which was introduced by Dirac in 1928. It's called second quantization. Of course, we already had a wave theory in Maxwell's theory, but now we make it quantum mechanically. And when you make wave theory quantum, it becomes particles. The same way as when you have particles, Newton motion, then it becomes waves when you quantize. So what is happening if you have an electromagnetic field is you can think about a standing wave being a normal standing wave with a vector direction of the electric field. You have a cosine wave in space, but then it's the magnitude of the field who becomes quantum mechanical, who gets the operator character. And this A and A dagger are like the raising and lowering operators of a harmonic oscillator. So this is like a position coordinate. And when the position of a harmonic oscillator swings back and forth, that's the same thing as the electromagnetic field having an amplitude that swings back and forth harmonically with time. And the energy of this field, which is related to the square of the electric field, gets this A dagger A part, which is quantized in units of 1. So therefore you get 1, 2, 3, 4, 5. That's the photon number corresponding, of course, to Planck's theory, counting the quanta of the photons. So in quantum optics, there's really two superposition principles at play at the same time. There's the wave superposition, the cosine waves that you can add as you like, but then there's also the quantum interference, which is this harmonic oscillator who has quantum states, and you can make superposition of these quantum states. And since there can be many waves in this room, for example, we can have light of any color, any wavelength, any propagation direction. You have infinitely many spatial waves, and then you have also in principle up to infinitely many photons occupying these infinitely many waves. So it's actually very complicated. It's quantum field theory. But in quantum optics, we often restrict, sometimes allowed, sometimes not exactly, the analysis to maybe a few modes or a single mode of the light field, and then we are concerned mostly about the dynamics of this single harmonic oscillator. Now, this is a nice story, and the quantum optics was developed around this, but there was also a kind of funny other consequence of quantum mechanics, and that is, I call it the exit of the quantum theory of light, because the Bohr's frequency condition was motivated by Planck's energy quanta. You needed the energy gaps between the electronic states to explain why the photons coming out had certain frequencies. But as soon as you quantize the matter, then the Schrödinger equation is actually going to give you, of course, the eigenstates here. And if you want to resonantly drive the transitions in an atom, you don't need a photon coming in with exactly that energy. You just need a monochromatic periodic drive. A classical field would also excite the atom resonantly, right? So if you have a system which has discrete eigenstates, a classical drive on that system will also drive it. Periodic term in the Schrödinger equation with the right frequency will excite the electron in the atom. So you don't need the photon to explain the transitions between Bohr's orbits or the new Schrödinger eigenstate. And it's not going to be jumps anymore. It's actually just the solution of the Schrödinger wave function or the Schrödinger equation, which is continuous in time, that explains these transitions, how they take place. So there's actually no need or no place for quantum jumps anymore. And Bohr was himself pretty unhappy around 1928, and he wrote a paper with John Slater and Hans Kramers, where he complained, so to speak, about this discontinuity that was in the original quantum jump idea, but not being necessary anymore because the Schrödinger equation is such a smooth equation and the wave theory is such a smooth theory. And most effects can in fact be described by classical fields. Of course, it doesn't mean that light is not quantum. We have a quantum theory for light, but many phenomena don't need the quantized nature of light to be explained. So there was even a whole school of neoclassical theories of light that was booming in the 1950s, but it's actually still active today. There are serious scientists, professors in good universities who believe that all optical phenomena can be described by noisy classical fields. I mean, somebody is shaking their head. It's not a very effective theory, but it's always good to ask questions.
Why does the counter go click?
Well, I'll tell you why the counter goes click. Okay, because that actually doesn't need the light to be quantized. So let's go into quantum optics now. And so I think many quantum optics textbook put a birthmark on quantum optics actually being the explanation of a non-quantum effect, namely an observatory, stellar observatory measurements that were done by Hanbury, Brown, and Twiss in the 1950s. So here you see two satellite disks looking into space, and they're going to receive signals from an object in space. And that signal you receive is going to be a noisy signal because it's not a laser that emits the light down on your disk. It's a noisy thermal light source, the surface of a star. And you have two disks, so therefore they receive probably the same signal but with some time delay. And you want to measure that time delay, and now I'm cheating because I'm actually showing the same figure twice. So now we're just going to move one, and then you can see it's the same one, and you can also see now all the structures are aligned with each other. And the amount of time I had to shift this one with respect to the other one is the delay in arrival time to those two detectors, and that's what you need in your astronomy application. And the way to actually do this, not by the eye, is that you take the two signals and then you technically just multiply them together, but you apply a time delay on one of them. And then this quantity here, averaged over time, will be maximum when that time delay is just the right one, because that's where all the spikes and valleys are on top of each other, and then you're going to get the maximum variance in that particular signal. But if you don't take that exact point, but you take any other thing, then you're going to get this falling curve, which shows that they get more and more uncorrelated, and if these are completely random in time with respect to each other, you just get the product of the mean value, which is of course less than the mean value of the square. So that was nice. That's pretty easy to explain. And I think physicists were taken a little bit aback by the fact that they had not even considering what this function would look like and how you calculate that. So there was immediately attempts made to understand what light sources give rise to which kind of dependencies of this function. And a lot of this can be done classically. So there's a theory of counting these photons, but some of it also involves better understanding of the quantum theory of what we're doing when we detect photons. And this is what Roy Glauber did in the early 60s. And it was also realized that the fluctuations here, the character of these fluctuations may actually prove the quantization of the light. And that's very exciting because it's measurement records, so it's actually classical records, but the way the statistics are in these records can prove the quantum nature of the source of these measurements. So going from being something that people would even claim could be described purely classically, light was now the most quantum kid on the block, actually, because we have this very clean signature of quantum effects. And Klaus, who just got the Nobel Prize, of course, for the famous Klaus experiment, was one of the first experimentalists to measure some of these correlations, and Jeff Kimball have measured similar correlations. And it's very interesting. We want now to understand what's the quantum version of this object up here, because there's a process in measuring these clicks, and then there's what is the statistical prediction for these guys if I have a known light source. And that was the theory that was developed by Glauber and his successors in the 1960s. And I think this is a fantastic thing. And it's when I read this paper by Glauber, I have to say this paper was written the same year as I was born. So it was not new physics when I read it, but I just never heard about it. And you open this article and you start, wow, what a good question. What a nice question. So now I'll share that question with you, and you have maybe already had quantum optics courses, so you already know the answer. But then dream yourself back to the time where you didn't know about this story, and then share with me the experience. I get happy every time I talk about this. In quantum mechanics, we describe systems by states, wave functions, or density matrices. We have observables which are described by operators, and they have eigenvalues, little a here, which are the numbers we actually measure. And there's a probability to get one of these values, which is given by the expansion of psi on the eigenstates of this operator. And you can calculate the mean. That's just the statistical mean. It's not a quantity in its own, but if you measure the value many, many times, then the weighted sum of the a's with these weight factors is what we call the mean value of A. And there's a projection postulate who also says that if you do a measurement, then after the measurement you actually put into the eigenstate of that operator. So this is quantum mechanics textbook material. So now here's a photo detection experiment. I send some light on a detector and the detector goes clicks. Here's the click record. It goes click and sometimes not click, and it's going to look like that. So I'll ask you a few simple questions. What's the state and what is the observable in this experiment? What eigenvalue is actually being measured here? What mean value is actually coming out of this measurement? And what is the state during and after the measurements that we see right here? And it's not so clear because, I mean, there's a light field and the light field is quantum, but what is this process? Am I really counting if there's 7 or 19 photons in the field by such a detection apparatus? Not really, because the detector says click and click, so sometimes it says maybe 1, and otherwise it says 0. So it's not really measuring the photon number in the field. It's randomly clicking. And that's a process that's going on here. It's not really a single measurement. It's something that happens also over time. Okay, so the answer is well known, and it's as old as me, because it was done by Glauber. So here's what I found so nice about this work, and what I find so nice about quantum optics, that we're not just taking a textbook and saying that the answer is here. We actually have to go down and look at what is the experiment, what is really happening in the experiment. And sometimes we have to include more components in the theory than we actually wanted to. So what you have to include, or what Glauber includes as a component, is the detector itself being a quantum mechanical machine. So when you detect light, you have light coming in, hitting some material in which there are some electrons. And these electrons can be excited. They can be ionized, or they can be lifted from a valence into a conduction band. But the actual physical process is that it takes the energy of one of these photons to lift the electron to a higher orbit, to a higher energy state. And what you really detect and what really goes click is these electrons. Okay? Maybe there's an avalanche effect, so the single electron is turned into 1,000 electrons by some amplification process, but it's still the release of that electron who is the step that we are really looking for. So if you want to understand what is happening in the photo detection experiment, we're actually doing the time evolution of the joint object of the quantum light state and the state of this detector. So in quantum mechanics, I have a state of the field and the detector, and to first order in time, dt, I have the same state minus, and then I put the Hamiltonian. And the relevant part of the Hamiltonian is the one where I have removed the photon with the A operator and excited the electron with this animal. I call it gamma dagger. It's just indicating that I'm lifting the energy of the detector state. Okay. So this is the physical state after a short time interval. And there's no click necessarily happening here, but if you look at the second part of this wave function, it's actually a component where I have lifted an electron. So this total state has a probability for containing a state with a free electron. And that's the one that you hear as a click in your detector, or that's the one who gets amplified to the click in your detector. So the measurement is this interaction process followed by looking whether there is a free electron or not. Okay? So we are not really measuring directly an observable of the field. We are witnessing the absorption of a photon. And what is happening here is that the field state changes. So we're not just measuring something, we are also not projecting the state, but we are acting upon the field part of the state by the annihilation operator. We are literally removing a photon. So it actually makes wonderful sense, but it's not the same as your good old textbook quantum measurement process. So that's what we do. You can ask what's the probability to get the click. That's of course the norm of that part of the wave function, right? Because the probability for components of the state is actually just the square norm of those parts of the wave function. So you can see here that this component, which is the same as the probability to get the click, which is proportional to the intensity, the measured intensity in your experiment, is then going to be the norm squared of the state. And if I take the detector part and separate that, then concerning the field, it becomes, well, I can write that state as a ket vector multiplied by the same bra vector. So then I get A psi and A dagger acting to the left on psi. So what you see here is actually the mean value of A dagger A. So the probability to get a click is actually proportional to the number of photons in the field. So when we say we measure the intensity, we measure the photon number, it's true, but it's not as the observable A dagger A that we are measuring. We are measuring a click, but that a click occurs with that probability. Okay, so it's kind of beautiful. I think it's nice. I mean, I was so happy when I read this. Wow, nice physics. It's really fun. And you have to do it a little bit yourself. It's not all in the textbook. Of course, Glauber already did it, so it was an easy task for me just to read his article. But I think it's still really, really nice physics. So we are measuring the photon number in an average sense. And then you can ask what further happens in your detector record, because you can have a click at time t, and then you can have a later click at t plus tau. And if you want to have these intensity correlations, it's exactly about intensities at different times, and that's what we register if we have clicks at these different times. So then I have to do the excitation process of the medium down here, removing of a photon at time t, and then again at time t plus tau. And if I want to know what's the probability for this to happen, what I would ascribe to the intensity correlations, then I have to take the norm squared of that joint wave function here. That's the one who contains two free electrons liberated at those moments in time. And concerning the field part, you get this funny object. And that's a rule by Glauber that many people refer to. This is what Glauber says we have to do. If you want to measure any function of the electric field, then you take and express field operators or field quantities in terms of A and A dagger, and then you do this double dots here, which means normal ordering. Put all the A daggers to the left and let time increase towards the middle of that expression. Okay, and this is a rule that we are using, but it comes from the fact that the detector is removing a photon and later it removes a later photon. And if you take the square of that object, you get exactly all the A's to the right and A daggers to the left, and you get time increasing in the order because measurements happen in the course of time. So this is super nice, and Glauber allows us now to calculate these kind of quantities. Now, there are a few anecdotes I'd just like to point out when you measure in a light field. If there's a click and you have an n-photon state, then the annihilation operator is a step-down operator for the harmonic oscillator, so it brings you down to n-1. So you have one photon less. Okay. So if you have this number state, there's a probability for the click. The probability for the second click is smaller, because now there's n-1 photons left, so that probability will go like n-1. So that leads ultimately to what we call anti-bunching, that there's an anti-correlation. If there's a click, there's a lower probability to get the next click from such a state. If you have a thermal state, then for all the n, what is happening at a click is that you go down to n-1, but you see there's a prefactor here, and this prefactor is large for large n and small for small n. So actually the probability for having high photon number states occupied grows if you remove a photon. So if you have a thermal state of light and you detect one photon, the remaining state has more photons than before you removed one. That's also nice, isn't it? But that's how quantum mechanics works. That's how probability theory sometimes works. So actually, by detecting one photon, the mean photon number grows. So there you will see what we call bunching. If you have one click, there's likely to be another click happening very soon. And then there's the magic coherent states, sometimes called Glauber coherent states. They are eigenstates of the annihilation operator. So that means that when you get a click with a certain probability, the second click will occur with exactly the same probability. Then it looks like a classical field, which doesn't suffer any losses when you are reading the value of the field. So this kind of observation, and many more of course, led to an interest in light sources, non-classical states of light who show anti-bunching and whatnot, squeezing and many other properties. So just having realized that we need this kind of theory to describe light detection also leads to, wow, and what can we now do? Can we do more precise measurements and whatnot? And Glauber here accounts for all of this, signal rates, probabilities, correlation. And it's very interesting because when you read his paper, he never refers to a quantum measurement problem. He's an anti-philosopher, but he's one of the best physicists we know in this field. He's just so smart. But he doesn't want to turn this into a ichthyosaur issue. I mean, there's not a philosophical issue, what happens to the quantum state of the light. These anecdotes, there's nothing mysterious about them. It's just a technical way to calculate these correlations. But in some sense, you might say that measuring these correlations witness that there is this back action taking place. There is this effect on the quantum state of detecting one photon to actually apply this operator. So the conditional dynamics or the fact that quantum states change when you look at the system is very inherent in this formalism, but it is never turned philosophical by Glauber. It's just, this is just a rule and it's just what we calculate. Now, we have lots and lots of applications. This is here from Boulder, Dave Wineland's group with trapped ions. This is Serge Roche in Paris, who traps microwave fields, studying single quantum systems, the ichthyosaur in the lab. And of course, we have, I call bits and pieces. That's all the solid state junk that you find optical. No, I have deep respect. I love these systems. These are much better quantum optical systems than the atoms are. They have stronger couplings. They have wonderful properties. You can solder them together, and you can get the same two-level systems, harmonic oscillators and whatnot. It's really fascinating. And a lot of the same theories can be, of course, transferred and sometimes even more easily studied on that side here. And the ability to control quantum systems is, of course, absolutely inherent in all these systems, and some of these are quantum computer candidates too, of course. So it's a treasure box for fantastic physics. And we have this atomic fluorescence and new light sources now to quantum centers, quantum memories, quantum bits, which is a great field, but still has this foundational character that we always have to remember what is a measurement and what kind of dynamics do we have in the system when we're looking at a quantum system. So I'd like to now switch gear and come to the more modern times. Where we are really talking about the evolution of the single quantum system. And it doesn't have to be a light field anymore, it could actually be anything. So here I've drawn the ichthyosaur, and the quantum system is often controllable by the Hamiltonian, the fields you apply to your atoms to excite them, for example. But then there's this ability to detect emission of signals, for example, photons emitted by atoms in resonance fluorescence. And when I have a click down here, something happens to the state of the atom, okay? Because I know that there's a photon emitted, I therefore also know that there's a photon lost from the system, and I therefore also know that the atom is now in its ground state, for example. So this measurement on a single quantum system imply collapse of wave functions or back action or state reduction, and it's not all necessarily described by the projection postulate. Like in Glauber's theory, it can be described by the action of a lowering operator, the one who actually brings the atom to the lower energy state, or the system to the lower energy state, compatible with you seeing energy leave the system. And this time evolution is non-unitary, non-linear, and non-local. It's sometimes very counterintuitive what is precisely happening, but of course that's also what makes it a resource for exotic dynamics. Niels Bohr commented about it in 1927. There's a famous Solvay conference where he's fighting with Einstein a lot. This was easier at the Como lecture because Einstein was not there. So here he comments that when these measurements happen, there's a complete rupture in the causal description of the dynamical behavior of the system. And there is, in this Como lecture, actually the beginning of what became the Copenhagen interpretation of quantum mechanics, that these states are states of knowledge, and it's actually not the system dynamical behavior, but it's my knowledge about the system who changes when I do the measurement. But that's for another talk. I'd like to show you something that I contributed to, and actually this is the stuff that we discussed here at Gila when Peter Soller organized the meeting, and Peter made big contributions to this field too. So we were really looking at photo detection process. I'll look here at an atom, and this is an atom who is described by a quantum state, a superposition of ground and excited state, and after a very short moment of time, the excited state atom has a small probability amplitude for actually having gone into the ground state and emitted a photon. So that it can also still be excited. So this is why there's a little black dot up here. So with a certain fraction probability, it's still there, but with a small probability, this has turned into a ground state atom with a photon leaving. So this is a picture, this is the formula, superposition of ground and excited state with 0 photon present, a time evolution happening to this state because of the energy difference, and then a little bit of amplitude slowly emerging on the ground state atom with 1 photon leaving in some different direction. And I apologize for the sum of all these lambdas, but that's because the photon could leave in any direction and with a range of different frequencies. So what we did in quantum optics for a long time was that we were looking at average behavior. And the average behavior of the atom is the probability to be in the ground state or the probability to be in the excited state. It's what we call the reduced density matrix. I'm actually just incoherently adding the ground state population being the sum of that blob, and the excited state being the sum of this one, and actually 0 coming from over here. And I'm putting on sunglasses. I'm not really seeing the photon. I'm just adding populations in this picture. But what you could also do, and that's more in the style of Glauber, is you could actually pretend that we detect these photons. So now if you look at this state, it has a 0 photon component and a 1 photon component. So if I'm detecting a photon, it cannot possibly come from the left-hand side. It has to come from the right-hand side. So if the detector goes click, it means I have that component of the wave function. The atom is definitely in the ground state, and what you see here is the ground state atom. The blob is big again because I renormalized the state. But I could also have seen no photon. And if I see no photon, then I'm in this part of the wave function. And that's, of course, the one where there is no photon. I still have a superposition of A and B. So one observation is that this is a measurement process that doesn't put you in 2 orthogonal states, depending on the outcome. It puts you in the state 0 because you measured the photon state, which is orthogonal to the 0 photon state. But the atomic states can have any relationship to each other. Okay. And then there's another little thing happening, and that is you have to remember that this probability here actually came from the excited state part. So this A and B, they don't add up to 1 unit norm. The B here has been reduced, and when I renormalize the state, it still represents a small reduction of this probability and an increase in that one. So even if you don't get any click from this device, the atom is more in the ground state after you have been looking at it and seeing no photon. But if you see a photon, it's definitely in the ground state. This is a analysis of what this measurement would do, but funnily enough, we can also argue that the average behavior from this reduced density matrix is exactly what you get on average if you just simulate doing either this or this in these measurements. So this is a stochastic, we call it Monte Carlo wave functions, because you are drawing random numbers to choose whether you emit, go to the ground state, or you make this tiny reduction and renormalize the state. And many people worked on that. Also, people in this room have contributed original ideas to this. It's a really funny, interesting methods to work on. And we discussed at that time with Jean Dalibard and Yvan Castin this as a method intended mostly to simulate effectively the master equations, because they can sometimes be large and complicated. If the system has not only 2 states but 1,000 states, there's 1,000 times 1,000 elements in such a matrix. It's really big, it's really complicated. While the wave functions are again, of course, 1,000 times smaller, so they could be simulated. Yeah?
Can you just elaborate a little bit? I'm confused about part of the wave function that's multiplying the vacuum of photons.
Yeah.
Is there some other piece of the radiation or Coulomb field that you just didn't diagonalize the atom levels? Like normally the photons are the ones that are driving the coupling.
Oh, yes.
Unless you didn't diagonalize.
Right, yeah, thank you very much. How was this state made in the first place, and how could it be made in a running time?
Some other field.
Exactly true. So in fact, either we could imagine that we had prepared the state by some incident laser field, but you can actually also have a Hamiltonian part of the system, a Schrödinger equation, where it's a direct driving term between those two. And that would be described exactly as you say by photons, but that would be a beam of light living in a very particular mode of the light field. And to be very precise, that should also be quantized. But there's actually there's a mathematical transformation, it's called the Mollo transformation, who actually allows us to replace that by a 2x2 coupling matrix here with a number in it. So that's an exact mathematical translation of what it means to be excited by a coherent state of light. It's the same as being excited by.
Strictly speaking, there's a photon.
Yeah.
It's because you're just describing the other field that's producing this Rabi by classical.
Exactly right. Exactly. So there can be Rabi oscillations on top of the thing I just described here. This is only describing the decay part, and then if I'm adding to this Rabi oscillations, then you're going to see the picture I show over here, where the atom is in a ground state, and now it does Rabi oscillations up and down, and then from every now and then it's interrupted by jumps back into the ground state. And if you do it just on a single realization, these jumps happen at random. If you do it 100 times, they happen at hundreds of different times, so therefore the average is going to look like damped Rabi oscillations here. So this is the driving by such a Hamiltonian. So I was very happy as a Dane to actually work on this, because these are Niels Bohr's quantum jumps. But when Bohr introduced them in 1913, he says they happen by themselves and then the atom emits light. But here it's actually the other way around. It's us detecting the light emitted, and then it happens to the quantum state as a consequence of this measurement back action. But nonetheless, it's the same thing. We are jumping the atom to the ground state at frequent intervals. So it's a very nice thing, and it works in quantum mechanics. Now, you can actually ask yourself, do these jumps really happen? And that's a little bit the philosophical question, Einstein's question. Does this really happen or not? And of course, it happens when we look, because then it's a kind of almost definition. There was this detection of the photon, therefore there's a removal of that energy from the system. But what if I don't have a detector? Do these emission events still occur at these discrete moments of time? And there's no real room in the theory to say where it should come from, because it's only measurements in quantum mechanics who have this abrupt character. But of course, it could still be that they would happen. I think a good argument against it is that you don't have to detect photons by counting. You can also mix such a weak field from the atom with a strong field and split it on a beam splitter. And then what you measure are now very strong, slightly noisy interference signals, where what the real observable up here is the intensity of this beam, which is a strong amplitude beta plus the annihilation operator coming from down here. So that intensity is going to be dominated by this strong field, but it's going to have a component which is proportional to A and A dagger. That is the field amplitude here. And this is actually a way to measure field amplitude by interference with another field. So if you actually have an experiment where you do this thing, the measurement back action on the system is going to be weak and stochastic and happen all the time. So could we say that this is also happening if we don't look? That's very unlikely to be true, because it could be that we were looking this way, and then this is actually what should happen, a stochastic evolution of the system, because you get many, many clicks who have a tiny back action on the system. So the jumping or the jittering of this atomic state is a consequence of actual and not hypothetical measurements. And if I'm a theorist and I'm claiming that we do quantum jumps, it's because I'm talking about what I would have had if I was actually doing a counting experiment. While if I was going to do a homodyne detection experiment, I would say that there's a noisy, fluctuating property of the quantum state, but continuous but stochastic in time. And this is actually to some extent related to the famous EPR paradox, Einstein, Podolsky, Rosen, because what happens to this atom depends on how we detect the photon. And the way I detect the photon determines what is the devolution of the atomic state. And that's, of course, very much like the two photons in a space experiment and in the old EPR paradox.
What do you measure in a homodyne?
You're measuring the intensity again, but it's an intensity of the interfering signal of a strong field and this weak field. So effectively, you're measuring a Bohring intensity, which is just a strong field intensity. But the really important signal is this quantity, which is the interference term, and that cross term is the amplitude of the weak field. So you're measuring the amplitude instead of the intensity of the fluorescent signal. And this is actually more or less the only thing you can do in the microwave regime. So superconducting qubits are not being read out by photon counting, but actually by this kind of homodyne field amplitude measurement. So some examples of probe quantum systems that I like, which is not the counting thing, but just a beautiful experiment, is Serge Roche in Paris. He traps a quantum field between two mirrors, and then he sends atoms through. And then every atom here picks up a small phase shift per photon, pi08 phase shift per photon in this cavity. So that means that if there's 0 photon or 1 photon or 2 photon, the atomic state will pick up small phase shifts, but it will not go into orthogonal states. So you can't really see the difference between 0 or 1 or 2 photons. But if I send really many of them, you can see the difference, because if there's no photon, you come out in the same state with 100% probability. If there's 1 photon, you come out in the same state but with 96% probability. And out of hundreds or maybe thousands of experiments, you can actually see the difference between 100% and 96%. And the same all the way down to 8 photon states. So here's an experiment actually from a Roche group where they send in about 100 atoms, and then they see the conditional state of the field ranging from being unknown number of photons to being definitely, or very high probability, 7 photons in that cavity at that time. If they do it again, they get 5 the next time and 3 the next time. But this is the way they learn what's the photon number in this cavity. And if they keep measuring over 10,000 atoms, then they will also see how the photon number changes over time. So the most likely value, which is 5 here, changes to 4, then to 3, then to 2. And that's just the leakage of the photons out of this cavity, which is here being monitored as discrete steps in the photon number. Average theories would say it leaks out exponentially. But if you're looking at something that decays, it's actually going to decay in steps. If you're looking at a nucleus, has it decayed or not? The answer is yes, I have decayed, or no, I have not decayed. It's only on average that you get the exponential decay. So here it's the same thing, that the exponential decay comes out as these staircase studies here. Now, just to share one thing with you, just a kind of question. I've been simulating this kind of dynamics for years for different systems, also with students, many projects. And the story is that when I'm doing my measurement record, I condition my state on it. So this density matrix symbol here just reflects how I know what is the state of the system at any moment in time as a function of the measurement record that I had so far. Now, at the end of the day, I've actually finished all my measurements. I'm going to submit the paper at time big T, because now I've finished doing the experiment. And I always ask myself, do I know more at this later time about the state at the earlier time? So imagine you have a cat, and you can't find your cat. You're running around your house, you're looking for the cat. And then, of course, when you find it, you know where it is, right? So now I know where's the cat. You probably also know where was the cat, because if it's a lazy cat, it has been in the same place all the time. So when you learn something by measurement, you're also learning something about values in the past. And how do we formulate that? And I don't want to show you the technical details, but I just said that it was a big question. I just wanted to know what it is. And then we finally made a theory for it. And there are equivalent theories also in classical estimation theories, but we call this the past quantum state, because it's the assignment of the state, quantum state of the system at an earlier moment in time, conditioned on measurements you did both before and after. Okay. Come and ask me if you want to know how it works. It's a very fun little theory. I just want to show you how well it works. And so this is the data I showed you before. So I have measured 10,000 atoms, and I want to know what was the state of the photon field around this moment in time, or any other moment in time. So we asked characterize, can we have all your raw data? And then we do our theory analysis of what was the state. So this is just standard quantum mechanics, but it's maybe a non-standard question that we're answering. And here's the answer. So we are using 2 matrices, one that is governed by the earlier measurement, one that's governed by the later one, and this is the predicted or retrodicted dynamics of the photon number in the cavity. So you see there's no uncertainty. These places where this blue curve is not exactly 1, it's actually much closer to 1. And there's not all these little spikes here, and that's really because they're smoothened out when you know after the fact that this was not a dip in this probability. It was just a statistical fluctuation, but the signal recovered and kept confirming that the photon number was actually 3. So this is a funny development of this theory that we made not so long time ago, and we have applied that to many different systems. And anybody who's measuring continuously in a system, please come to me and we can discuss how you can make this analysis of your experiment. It works for superconducting qubits and optomechanics and many other systems too. Now, we had a funny little experience. Sergio Ross published this in Nature. He probably even got the Nobel Prize. They probably mentioned this experiment also in the Nobel Prize nomination. There's one thing missing in his paper. He tells here what's the probability for the photon number to have these different values, but he doesn't show it's right. This is just what he thinks is the probability for the photon number to be 2. And nobody asked, but is the photon number really 2 here? Is he right, or is he just showing a curve that he thinks is right? And the answer is he only shows curves that he thinks is right. But it looks so nice that people said, wow, you can really track that. But in fact, we don't even know if it's right. We just know that it's an assignment. Now, we submitted this paper much more modestly to Physical Review A, and we had a really grumpy referee who said, this is very nice, but how can you be sure that it's right? And I was just laughing, because I was not begging to get the Nobel Prize in physics. I just wanted to show this theory, which is a standard theory. and there's nothing, it's just quantum mechanics. I mean, it's just showing what we know based on the measurement. But the referee was really insisting that this is not really confirming anything unless you show that it's really true that there was that photon number in the cavity. So anyway, so we asked the guys in the lab, please do the experiment again, and then have a guy sneak in at a moment, don't tell the other guys, but put a photon in the cavity at that moment in time. So a guy comes in, and at atom number 4000 is resonant with the cavity. There's no photon in the cavity. He puts one, bang, at this moment in time. And what you see as a red curve is the standard, this upper trace inference, how the photon number is 0, and then it grows up to being 1, but of course with some error bar. With a little bit of delay, because you have to accumulate statistics before you're really sure that there's a photon in this cavity. And our theory is the green curve. Okay, so we are using all the data, and it's just spot on. We say it's exactly atom number 4000 who delivered a photon into this cavity. And we didn't know why this was. Another guy on the other side of the table who did it, but we could pinpoint exactly what had happened. And that made the referee happy. Of course, I'm also happy, so thank you to the referee if he or she is here, because of course it was much nicer to say, look, I can see that something happened and know that it actually happened in the experiment. So this was a fun twist to this. Now, time is up. I know time is up. I just want to quickly show you one or two slides, which is a little bit funny. When you want to measure a quantity you don't know, for example, a parameter in your Hamiltonian, then one way to actually use exactly the same trajectory formalism to infer such a value is to note the fact that if it has one value or another value, you get different states. And if you get different states, you get different probabilities for the outcomes. So the state depends on that parameter, and the probability to get a data point D depends on that outcome. That's Bohr's rule, using different states. And if I actually measure a certain outcome, which is what you do in the lab, then if I know the probability of the data conditioned on theta, I also know the probability for theta being true conditioned on the data. That's called Bayes' rule, that you can invert these probabilities. So the quantum trajectory method, this Bohr rule application, actually allows us to take a full measurement record, and every time you get a click or no click in your detector, you are updating what is the most likely value in your Hamiltonian. So this is really working wonders, and it's nothing new that we have to do. We just have to run in parallel this stochastic equation, assuming different candidate values, and then we can follow over time who is the winner in this particular game here. So if I have this detector click record I showed you before, some detector clicks happening, it could be, well, of course, it's this Rabi oscillation dynamics with some clicks in between, but I don't know what is the Rabi frequency. If it has one value, then there's a click sometimes, and then oscillations in between. But of course, if it was a weaker Rabi frequency, the oscillations would be slower. The clicks still happen when I see them. So there's a click here just after 5 and some other clicks, but this could then be the dynamics. Or if it's higher, then it would look faster, but the clicks, of course, happen where the experimentalists saw them. So what I'm going to do now is I'm going to align these, and then the clicks are happening here and here and here and here. The probability to get these clicks is the excited state probability. So you can see this is how high is that star, how high is that star, how high is that star. And this is the probabilities for the other clicks. And I think with the naked eye, you can see that these probabilities are generally higher than the ones you see down here. So if you ask what is the most likely of these three values, it is by far that one who is the most likely Rabi frequency. And it's really based on every piece of information the experimentalist gives you. It's the time of the clicks. It's not only the number of clicks, it's the time of every click. So this is the winner. Here I have a click record with 50 clicks or so. And if I assume the Rabi frequency is unknown between 1 and 7 times the decay rate of the atom, completely uniform, then after just 2 handfuls of clicks, I almost know precisely what is the allowed Rabi frequency. It's a super fast filtering method for sensing. So I would argue that in all these continuous probing experiments, you should use this kind of trajectory description, and then you actually get to a nice understanding. Now we have tried to make some more general theory. What is the error bar going to be? I just advertised the papers, but I want to get to the end, and this is my last slide, so don't worry, Anna Maria, we'll finish now. Quantum mechanics is fantastic. I did not talk as much about Bohr as I like to talk about Niels Bohr. He was, of course, one of the pioneers or the big shots in putting out the interpretation of quantum mechanics. And this is a quote, something he said just within last week before he died. He said that if we should one day wake up and realize it was all just a dream, we would still have learned something. So I hope that's also true for this talk.
Can you hear me? Yes. Thank you for the fascinating colloquium. We are open for questions now.
Hey, thanks for the great colloquium. That was really interesting. So part of the way to use Bayes' rule is that you need to have some sort of priors in order
Yes.
to use it correctly. So then in the smoothing for was it the ENS experiment? So you had to for the second experiment where you had someone else add a photon to the cavity. As part of your prior, you had to know that someone was at some point going to add a photon.
Yes.
So if you tried to do the same procedure, but you didn't know how many photons people were going to add, would you, in some limit, reproduce the noisy plot?
It's a brilliant question because, I mean, and that also what makes Bayes' rule hard to apply. One thing is that the prior, even for your prior knowledge, is sometimes very important and it's hard to quantify. And the other thing is that anything that can happen also has to have a probability, because if it had probability 0, I could also not infer that it actually happened. So you are exactly right about that. And so we had to say, okay, promise us that you will, with a probability of 1 per mil, actually add a photon at any moment in time. And then that's what we put into the theory, that we had this thing that could happen. And then, of course, the measurement record gave it away. But actually, at every moment in time, we added it ourselves with a 1 per mil probability, and then the data ruled out that it had happened. But at that particular point, 4,000, the data did not rule out that it had happened, but actually confirmed that this is when it happened. We had a very funny thing also. So Serge made a beautiful experiment where he was allowing for, there's a Boltzmann finite temperature in the vacuum, in this chamber, where he's doing the experiment. So there's actually a rate for photons to leak into the experiment naturally. And if he cranks up the temperature a little bit, that rate is also higher. So then he's monitoring what he calls the birth and the death of the photon in the cavity, because he sees, just like the steps I showed you, he also sees steps going up. But then he did measurements where he only measured with a pi phase shift, not a pi over 8 phase shift. So he could actually only see the difference between even and odd photon numbers. And in the article he said, okay, that's because the temperature is low, sometimes 0, most of the time 0 photon, sometimes 1 photon. But there were some very short intervals in time where he thought it was 0. And when we did the analysis, it came out being 2. Okay, and of course we had the same data as him, but we had the before and after. So we knew that this was a short interval. And of course you don't know when you enter an interval of detection clicks that this is going to be a short one, because you haven't seen the end of it yet. And so I told him, I said, you know, there's not 0 here, it's actually 2. And he said, yeah, we always thought so, but we didn't have a way to argue why it's true. So of course, many of these things are intuitively also well understood, but you still need a formalism to describe it. And Bayes' rule is something you have to be careful about.
Thank you.
More questions? Didi.
It was a great talk, Klaus. Thanks a lot. I have a maybe related question, and that is, for example, if you look at the photons from an atom, you're not catching all of them.
Right.
So do you have to make some sort of fair sampling assumption as well?
Yes, that's again a very nice question. So in 91, 92, when we developed this, we wanted to assume perfect detectors, but we called them Gedanken measurements because it was only a mathematical trick to replace master equations, replace density matrices by pure states, and then sample over these guys. But then in the more modern times where we have all these single system experiments, this is now true quantition dynamics. And if you have a detector who has an efficiency of 60%, you know you're only going to see 60% of the photons, but you don't know which ones. And this we can model, right? And it becomes, again, a density matrix, because the unseen, the knowledge that they are detecting events I didn't see, just translates into being some mixed state dynamics. There is a rate for going to the ground state unobserved, so to speak. And so this we know how to do. And still we have to assume fair sampling if we want to go as far as disprove hidden variable theories. But in practice, of course, if your detector efficiency is 80%, it is equivalent to take 20% of the fluorescence signal off by a beam splitter and then analyze that situation. So that gives a new stochastic master equation. And all the sensing we actually do with stochastic master equations, because we cannot assume that we see everything. Yeah. But what is super hard is, of course, if your detector has dead time issues, if there's a finite bandwidth, so there's some kind of electronic processing going on, because then we are breaking other assumptions about the detection. I mean, Maury did some nice work about frequency selective sensing at some point, and that's harder, right? Because you are not local in time anymore.
I just had a really brief comment. So going back to 1992, one of the things I thought was most interesting was at that time there were like different perspectives. Yes. There were people doing things like quantum state diffusion and extensions to the Schrödinger equation, and Howard Carmichael, for example, doing quantum trajectories, and there were a number of different perspectives.
Right.
And what I thought was so interesting was that they all coalesced essentially into this same picture of just conditional dynamics based on what you measure. So.
And thank you for that remark, Maurice. So I mean, it is exactly true that at exactly the same time, or within very few years, Howard Carmichael, he said, I want to understand why measurement records are noisy, and I want to understand why there's anti-bunching, for example. And for that, he needed the source to have this dynamics. He needed the removal of the photon to cause a break in the fluorescence to happen after that. So he realized that wave function together with the detection record form a joint object where the record is conditioned from the state by Born's rule, but the state is conditioned by the record by the measurement back action. And that's a beautiful concept, and I always felt that he was so much smarter than we were, because that was a much deeper concept than the technical thing we did. And then there was Hegerfeld in Göttingen, who had a similar theory, not just explaining, but explaining the shelving scheme and quantum jumps that you see with trapped ions. And then I really have to say that 10 years before all of this, there was a Russian mathematical physicist, Slava Belavkin, and he had developed all of this also, but in a more mathematical sense. And I feel very honored, because he always referred to me as an experimentalist when he talked about me. And he visited, and I have to say, he visited me for half a year, and we wrote a paper together, but he still always referred to me as an experimentalist. And so this existed, and even the base rule stuff I mentioned to you at the end was also done by Slava Belavkin, but in a hard to read manner in around 1980. So these things have been around, and I should also say that when Peter Soller organized this meeting here in the mid-1990s, it was because he had also had ideas about these random jumps, but his starting point had been more like Glauber. Let's calculate these correlations. And when you know all the multi-time correlations, then you can also simulate them and make the click record. So he was kind of going the complicated way from the big density matrix theory to construct the coincidence rates and then simulating them by clicks. While I think that the approach by Carmichael and by us and Hegerfeld was more, we can actually understand any moment in time that it's only Born's rule we are talking about.